Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is resistive complex impedance. Our objective is to learn how to represent resistors as complex impedances for the purposes of AC circuit analysis. This lecture operates on the presumption that the viewer has more than a passing familiarity with complex numbers, as illustrated in the previous lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. You are no doubt familiar with the DC response of resistors, capacitors, and inductors. In summary, resistors follow Ohm's law, a phenomenon that relates voltage, current, and resistance. Resistors dissipate all power supplied to them in the form of heat and are not energy storage devices. Even our initial discussions of resistors and sinusoidal AC sources demonstrated that resistors consistently follow Ohm's law and voltage and current are in phase with one another. Capacitors and inductors, in contrast, are reactive elements and can momentarily store and return energy. As such, the reactive nature of these energy storage devices need to be accounted for. Recall from our discussions about the time-variant DC response of capacitors that initially uncharged capacitors experience a current spike followed by rising voltage. This behavior can be summarized as current leading voltage for capacitive elements, and that the current spike occurs before rising voltage. The time constant established by the capacitive circuit under inspection determines how slow or fast this exchange of energy occurs. Similarly, recall from our discussion on the time-variant DC response of inductors that inductors with no established magnetic field experience a voltage spike followed by rising current. This behavior can be summarized as current lagging voltage for inductive elements, and that the current rise occurs only after the voltage spike. As with capacitors, the time constant established by the inductive circuit under inspection determines how slow or fast this exchange of energy occurs. For purposes of time-variant DC analysis, we never really explored beyond these horizons. If, however, we push the boundaries into circuits incorporating sinusoidal AC sources that continuously change, there is no initial nor steady state, and reactive elements like capacitors and inductors will continuously store and discharge energy on a cyclical basis. Despite this constant interchange, one truth remains constant. Current will be in phase with voltage for purely resistive elements. Current will continuously lead voltage for purely capacitive elements, and current will continuously lag voltage for inductive elements. We'll examine this phase-shifted response in greater detail in later lectures. The reactive nature of elements in AC circuit analysis are accounted for using one of two tools. One, either time-consuming calculus-based techniques, or two, simple algebraic techniques making use of complex numbers. My choice is to employ complex numbers. Bottom line up front, resistors, capacitors, and inductors can be represented as complex impedances, where impedance is a term quasi-equivalent to resistance for the purposes of DC circuit analysis. Only the complex nature of impedance includes time-shifted effects for purposes of AC circuit analysis. The true nature of complex impedance will only become apparent in later lectures. However, we at least need to learn to calculate complex impedance for now. Resistors, when represented as complex impedances, are elements entirely in the positive horizontal real x-plane. Frequency of the AC source has no effect on the magnitude of the resistive complex impedance. As such, a resistor represented as a complex impedance can be calculated as the resistance value at an angle of 0 when represented using polar format. When depicted in the impedance domain, resistors exist solely on the real horizontal x-axis, proportional to the resistor's magnitude. If you wanted to represent resistive complex impedance using rectangular format, it would be proportional to R, existing solely in the real horizontal x-axis, plus or minus J times 0. Since we're representing the complex impedance of resistors using a complex number, note the value ZR includes an overbar, indicating this isn't just a magnitude, but also includes a direction.